So our next speakers are Daniel Weber and Vlad Tsyrklevich, and they are going to tell us about the Equational Theories Project. Over to you.
Thank you. So my name is Vlad Tsyrklevich, and Daniel Weber and I will be speaking about the Equational Theories Project. As Kevin just said, this presentation includes some links throughout for anyone that's interested in digging in further. So I've included the link to the slides at the bottom. It'll also be on Zulip later. And I'm going to start off giving an overview of the project. And afterwards, Daniel will talk about automated theorem provers, proof automation, and infinite model construction. So the very first thing I want to do is mention that this project is a group effort. Almost 50 people contributed to the GitHub repository. And not everybody that was involved in the project uses GitHub. There were a number of contributors who just contributed things on Zulip. I also included the list of authors for the paper that's being written about the results of the project. Unfortunately, that list is incomplete as the paper is still in progress. So I just wanted to say that a lot of people contributed to the project, and we're presenting about the works of a whole group of people. So it's not just our work. So what is the Equational Theories Project? Well, at the end of September last year, Terence Tao announced a new project on his blog. And the gist of his blog post is that mathematicians tend to work in small, trusted groups. It's hard to work with the public or with AI due to the risk of any error invalidating your results. But interactive theorem provers can counteract the risk of errors. And while many formalization projects have tended to focus on formalizing existing results, proof assistance can also be used for exploring new problems. And the blog post announced a pilot project with two goals: to study a specific mathematical problem, but also to explore how to collaboratively work on novel mathematics in a public setting using lean formalization as the medium. So the idea is to collaboratively work on research, kind of like polymath, with the additional correctness guarantees from formalizing the results. And the recent completion of the Busy Beaver Challenge is an example of this style of project. The Busy Beaver Challenge was a collaborative online research project that studied and formalized a result about Turing machines in Coq. And so Terence's idea was that rather than trying to work on an individual problem, crowdsourcing a class of problems seemed like a good approach for this style of project. This makes it easy for many people to participate, including those without deep knowledge of a specific subject area. And the problem he chose in universal algebra is general enough to be widely accessible. And as I showed on the previous slide, and in the end, there were many contributors from a number of different backgrounds, from lean experts working for the FRO to those with no experience in lean whatsoever, from accomplished mathematicians to people with no graduate level training in math. So before describing the research goal of the project, I have to set down a number of definitions. So a magma is just a set M with a closed binary operation. I'll write this operation using a diamond throughout the presentation. A magma is an algebraic structure, just like a group or a monoid, except it has no constraints whatsoever on the operation. In this sense, it's not very interesting unless we actually add some constraints to study. So we can consider magmas with an additional constraint, an equational law, which is just an equality of terms containing variables and potentially making use of the magma operation. So one example is the commutative law, which I've written for all x and y in the set M, x diamond y equals y diamond x. In all of the equations studied by the project, the variables x and y in this case are always free variables. They do not refer to individual elements of the set M. So going forward, I'll write equations without the for all quantifier. I'll just write x diamond y equals y diamond x, but the variables are implicitly universally quantified. And the Equational Theories Project only studies magmas that satisfy one equational law. We're not looking at magmas that satisfy multiple equational laws. Then I just give some example equational laws. Note that the project has numbered these equations to give us consistent ways to reference them. The numbers themselves don't have meaning. So equation 1 is the trivial equation, x equals x. Every single magma satisfies this equation. The equation below it, equation 2, x equals y, is its opposite. The only magmas that satisfy the equation x equals y are magmas over the empty set or the set with one element. This equation can't satisfy any other non-trivial magmas. And I give two other examples below that just for illustration. Equation 46 is an equation that defines magmas, where x diamond y is a constant value for all values x and y. And the last one is the associative law. Note that since the magma operation is not known to be associative or commutative, parentheses and order matter when writing equations. And the last definitions that we need are for implication or refutation. We are interested in whether all magmas satisfying one equation also satisfy another equation. We say equation A implies equation B if every model of equation A is also a model of equation B. If this is not true, we say equation A refutes equation B. And I'm going to give you an example now to make this concrete. I define a magma over the set 0, 1 with the operation defined by the table on the right. This magma satisfies equation 3, which is x equals x diamond x. Remember that x is universally quantified, so this is saying that 0 equals 0 diamond 0 and 1 equals 1 diamond 1. Looking at the table, this is true, so this is a model of equation 3. Furthermore, I claim this model does not satisfy equation 4, x equals x diamond y. If I pick x equals 0 and y equals 1, we should have 0 equals 0 diamond 1, but this isn't true. So it's not a model of equation 4. And therefore, since there is a model of equation 3 that is not a model of equation 4, we say that equation 3 refutes equation 4. Looking in the opposite direction, I can prove that equation 4 implies equation 3. The proof is straightforward. If we have a magma that satisfies the equation x equals x diamond y for all x and y, then set y equal to x, and we get that x equals x diamond x. So a magma that satisfies the equation x equals x diamond y must also satisfy x equals x diamond x. This is a fairly simple example, but the arguments I used are more general. Almost all refutations in the Equational Theories project were proven by constructing explicit counterexamples like I just did. And for implications, all implications are proven using syntactic rewriting like above. Obviously, the rewriting could be more involved and complex than this. And so with the definitions out of the way, I can explain the research goal of the Equational Theories project. The goal of the project is to fully determine the implication graph for all equational laws that make use of up to 4 operations. Or, stated otherwise, determine whether every equation up to 4 operations does or does not imply every other equation. We count operations on both the left and right-hand sides of the equation. So you can generate an infinite number of equations with up to 4 operations, x equals x, y equals y, z equals z, etc. But normalizing the list of equations to get rid of obvious duplicate equations like x equals x and y equals y, or x equals y and y equals x, you're left with 4,694 equations with up to 4 operations. So that means that there's 4,694 squared pairs of equations, or about 22 million hypothetical implications or refutations to be determined to fully determine this graph. In practice, we don't have to prove all of these individually. Many equations are equivalent, and we can use transitivity and some other methods to reduce the number of statements that we have to prove. And we also have a concept of duality. For example, all magmas that satisfy x equals x diamond y satisfy x equals y diamond x if you flip the order of applying the magma operation, or visually if you flip the operation table on its diagonal axis. So in the end, the project actually consists of about 10,000 theorems in Lean, and Daniel will talk more about how we minimize proofs later. I'm going to talk a little bit about the organization of the project because I think some elements of it differ from other lean formalization projects, and I think it may be interesting to highlight how. For anyone familiar with Lean, we used familiar tools: Zulip, GitHub, continuous integration, Lean Blueprint. I also link a helpful log that Terence Tao maintained. He summarized results and Zulip discussions as they occurred. So it offers a historical perspective on the progression of the project, but also when people were working on different parts of the project or um, not following the project, not following the Zulip, which could be very active, it's kind of served as a point where everybody could go and see the progress and understand what was happening. The project also used new tooling developed by Pietro Monticone for managing the project. Maintainers create GitHub issues, and then participants can claim them. This reduces duplication of work by participants in the project and reduces management overhead, keeping track of claimed work for maintainers. We also made use of a custom attribute, equational underscore result. Proofs of implications or refutations in the project would add the equational result attribute, and this served three functions. First, it verified that theorem statements were well formed. Second, it enforced that tracked theorems were sorry-free. In contrast to other formalization projects, results are largely independent of one another, so sorry theorem statements aren't necessary or desirable. And lastly, it allowed us to export the known results to tooling outside of Lean. In addition to a given implication being unknown or proven, we also had a third category for tracking informal results. If we had an informal human proof or perhaps a machine-assisted proof that we did not yet know how to formalize, then this could be marked as a conjecture. These conjectures were Lean statements in the repository, so they're also collected and exported alongside the formalized results. And many implications and refutations went straight from unknown to Lean formalized without having been a conjecture. But it was a useful tool for tracking results and making sure participants didn't waste time working on solved problems, especially for um, refutations that took longer and were more difficult to formalize. And we have a tool called extract implications that extracts data about theorems and conjectures and exports them in some other format like JSON. This is run in CI, and then that data powers some custom web applications built specifically for the project. Lean custom tools were necessary because of the volume of data. No one can manually track 22 million pairs, and Lean Blueprint isn't really the correct tool for organizing this type of project. But the web applications were also useful because there are project participants with no Lean experience who don't have working development environments, but who did still make valuable contributions like novel informal proofs on Zulip. Having web applications outside of the IDE allows everyone to participate. And the web apps just ended up being a lot more useful than the scripts that they replaced. So I'll give a brief summary of the individual tools. The dashboard displays the high-level overview of the project, the total number of resolved, conjectured, and unknown implications. It also includes links and some other data about the high-level progress of the project. This entire page doesn't fit on a single slide, so I just captured this table, which I'll get back to later. The Equation Explorer is the primary tool to navigate the implication graph. Hopefully you can read it on the right. I have the page open for a specific equation. You can see its inbound and outbound implications and refutations. You can also see other members of that equations equivalence class. The page can include custom commentary for interesting equations and also links to other tools like Graffiti and the Finite Magma Explorer. It has quite a number of functions, so I won't describe all of the functionality, but this is the central tool for querying and looking at the graph. Graffiti visualizes the implication graph as a Hess diagram. So that means edges going upwards are implications, and another way to see it is that downward edges represent subset relationships. You can see some nodes with rounded edges that have multiple equations inside. Those are equivalence classes that are collapsed into a single node for clarity. Graffiti supports custom search parameters to visualize specific subsets of the graph, like I show here. It can also display the entire implication graph, but the complete graph is large and challenging to navigate. And lastly, the Finite Magma Explorer tests which equations a given finite magma satisfies or fails to satisfy. Maybe you can see that on the left, I've input the operation table from the example I gave earlier. And like in the example, you can see on the right that the magma defined by this operation table satisfies equation 3, but does not satisfy equation 4. The Finite Magma Explorer is aware of the finite implication graph. So if a magma is given that witnesses an unknown refutation in the repository, the tool actually notifies the user and provides instructions for how to contribute that result back to the GitHub repository. So with all the high-level organization and infrastructure of the project covered, what is the actual current status of the project? For the original research goal of the project, all but 30 refutations have been formalized. Of the 30 remaining refutations, all of them have informal proofs that are awaiting formalization. And we're not awaiting 30 different formalizations. There are actually only 3 remaining constructions to complete the graph. So in short, the project believes that it's fully determined the implication graph and the formalization is close to complete. Proving implications turned out to be much easier than proving refutations. Automated theorem provers, or ATPs, were able to resolve all positive implications and many refutations. Daniel finished formalizing the positive implications using automated theorem provers on day 9. But the work to finish proving refutations continued for almost another 2 months. Having completed the positive implications and the lowest hanging refutations, the implication graph was actually about 99.8% complete on day 9. But counting total transitive implications, by counting total transitive implications or refutations. But counting this way is a pretty poor measure of progress. You should really think about the log graph rather than kind of the normal graph. Most of the work was on the remaining several hundreds of unproven refutations, where some properties of the 2 equations made finding a satisfying countermodel to prove the refutation difficult. The last refutation was not informally resolved until day 57. So most of the work in the project was spent proving refutations, and then the continued work of completing formalizations afterwards. As you might expect, a number of the formalized proofs also had to be corrected. A number of the informal proofs also had to be corrected in the course of formalization. But automated theorem provers were not able to resolve all refutations. As the project progressed, the remaining refutations were harder and harder to resolve. And participants made extensive use of ATPs to guide their research. So not just having an automated theorem prover directly solve a given problem by finding a counterexample, but guiding them and using them interactively. The automated theorem prover could confirm or deny whether adding an additional hypothesis would invalidate a given avenue of attack, or the ATP could also be directed to explore specific parts of the search space that participants thought were likely to bear fruit. The use of ATPs in the project was quite extensive, even though I believe that most participants did not have prior experience using ATPs. So next, I'll describe a related problem that was also studied in the project. Some implications are true for all finite magmas, but not for magmas with infinite cardinality. In the original aim of the project, this would count as refutation, since there is some model of one equation that does not satisfy the other equation. And the proof would then generally, consist of constructing some infinite model to demonstrate that refutation. So if the original goal of the project was to resolve implications for all magmas, this introduces the question of what does the implication graph look like if we restrict ourselves to only finite magmas? I'll call the implication graph for finite and infinite magmas the general graph, which is what was previously studied. And this is in contrast to the finite graph of implications for only finite magmas. So it turns out that in almost all cases, the finite graph and the general graph are equivalent. Proving implications by syntactic rewriting, as I illustrated earlier, holds for both finite and infinite magmas. And for refutations, the project had proven the majority of them using finite magmas, with the remainder using infinite models or meta-theoretic arguments about confluence. One interesting thing about the finite graph is that in contrast to the general graph, proving implications is not quite as easy. Proving a finite implication is no longer a first-order problem that an automated theorem prover can solve out of the box. Outside of a few implications at the very, very beginning of the project, every implication for the general graph was proven using an automated theorem prover. But this wasn't the case for the finite graph. Most finite implications were still proven by making use of automated theorem provers, by giving the ATP the additional axiom that injectivity is equivalent to surjectivity, which is true for finite magmas. But there were a handful of proofs discovered by hand that made use of the fact that repeated function application in finite contexts is eventually periodic, and using this to establish an implication. This is one way that work on the finite graph differed from the general graph. In the case of the general graph, participants believed that the only remaining unknowns were all refutations after day 9. And for the finite graph, this was never clear if the potential implication or refutation was actually one or the other. Uh, working to Working to resolve the finite graph also led us to discover that we had used infinite constructions to prove a number of refutations where finite countermodels actually existed. Generally, the refutation was established using an infinite counterexample, because using an automated theorem prover to find a finite counterexample hadn't been fruitful earlier. So going back to address these cases meant refining methods or developing new tools to work on the most difficult to establish cases. And prior to the work on the finite graph beginning, the largest finite counterexample that was tracked in the repository was of order 32. But once the work to resolve the finite graph began, this led to a counterexample of order 232. Note that this is not the theoretically minimal size to prove that refutation. We're not sure what that is. It's just an illustration that going back to look at these cases led us to discover new phenomena. So what is the status of determining the finite implication graph? There is a single remaining unknown that is proven to be very stubborn. The remaining open question is whether equation 677, shown on the slide, implies or refutes equation 255. Note that the no proof number on the screen says 2, but finding a proof for this question would also lead to a proof for its dual. So equation 677 has relatively few models, so finding refutation by brute force has not proven practical. And many of the techniques developed during the project have not worked to resolve this question. Yeah, the work is to find a finite counterexample has only led to dead ends so far, and it's not been clear why equation 677 may imply to equation 255. So it's still open. And finally, I'll mention that a paper is currently being written to collect the results of the project. During the project, participants also thought up a number of questions that just interested them on Zulip and studied some of them just for fun. I'm not familiar with all of the questions to give a description of all of them here. I just included a few in the bullet points here. And that's my overview of the Equational Theories Project. Thanks for following along. With that, I'm going to hand off to Daniel.
Let me share the screen. Okay. Hello. On September last year, when I saw the project announced on the Lean Zulip, I was very interested in it and I started contributing. And I'm very excited to talk to you today about the results of the project and what methods we used in it. As Vlad mentioned, the Equational Theories Project is a project about figuring out all of the implications between the different equational laws up to order 4.
Just to say, I just
And
see a
now,
white screen. Is that correct?
yeah.
Okay, sorry.
And now we will talk about the techniques we used during it and what methods we used. Before I start, let me briefly introduce myself. I'm Daniel Weber. I'm a PhD student in computer science at Ben-Gurion University. I mostly work on cryptography, but I'm a big fan of Lean. So at the start of the project, we didn't have almost any implications, only the most trivial ones. And we wanted, but it was clear that because of the high number of implications we needed to maintain, that we needed some structure to maintain all of the implications and whether we have proved that they're false, and things like that. We also wanted to be able to automatically use transitivity. For positive implications, this means that if we know that A implies B and B implies C, then A must imply C. And for negative implications, it has two forms. If A implies B but A doesn't imply C, then B can't imply C. And if B implies C but A doesn't imply C, then A can't imply B. So for the positive implications, this is just building a directed graph and taking its transitive closure. For the negative implications, we built a representation graph. The representation graph has two copies of each law. It has x and x prime. And whenever we have an implication from x to y, we add two edges from y to x and from y prime to x prime. And whenever we have a refutation from x to y, we have an edge from x to y prime. Now, if we take the transitive closure of this representation graph, a path from x to y prime in the representation graph means that there is a refutation from x to y, and a path from y to x is a positive implication from x to y. On the Lean side, as Vlad has mentioned, we added the equational result attribute to store results that are relevant to the implication graph so we can process them later. And another interesting fact that we had is that oftentimes we have a single magma, and the magma has a list of laws it satisfies and a list of laws it doesn't satisfy. And this gives many implications at the same time, many anti-implications at the same time, because all of the laws it satisfies can't imply any of the laws it doesn't satisfy. So we created a custom syntax in Lean for that, the fact syntax, which states that the magma satisfies all of the laws in the first list, but doesn't satisfy any laws in the second list. And for the transitive closure, we added a dummy node, M. So for all laws in the first list, we added an edge from the law to the dummy node. And for all laws in the second list, we added an edge from the dummy node to the law prime. So this means that in the transitive closure, there's an edge for every pair of the laws. Another thing about the magmas, there are many anti-implications that are demonstrated in many different magmas. So we created a custom script that chooses which anti-implications to prove by which magma, such that we minimize total work needed to be done by the kernel for the verification. Okay, so after we had the infrastructure, we still had many proofs left to write. So we needed to start working on proof automation. At the start, even during the implementation of the infrastructure, we had many low-hanging fruits that we can take. For example, using simple rewrites or using a fixed proof script that just applies the equation multiple times. This managed to take a fair number of implications. For the rest of the implications, we used more sophisticated automation. So to talk a bit about automation, we can classify automation in this context to two categories. We have Lean tactics that are very tightly integrated with Lean and produce proofs in Lean. And we also have ATPs that are independent of Lean. They're very large. They existed before Lean, and because they are so large and their kernel is much larger than Lean, we don't want it to be part of our trusted code base. So we translate the proofs the ATP produces to Lean. So for using ATPs in Lean, we came up with a classification to three categories. The first category is ATPs that are implemented directly in Lean as a tactic. One example of this is ISOP. The second category is when a Lean tactic uses an external ATP and then translates its output to the Lean term. For example, using the BV decides tactic. This is a tactic that decides Boolean equations using by calling an external subsolver and then turning its proof to Lean. And the third approach is having an external script which calls the ATP, parses its output, and produces the Lean text. The Lean text that the Lean interprets later, which is a code actually. So this is not very user friendly because for other users you have to directly edit the script and copy the code, and it's high maintenance. However, it was the easiest to implement, so this is what we mostly use in this project for the new automations. So the ATP we use the most is Vampire. Vampire is the state-of-the-art theorem prover for first-order logic, and the deduction it implements is known as superposition calculus, which is a generalization of resolution that can handle equalities. So the deductive step for it works like this. If we know that we have L is equal to R, and we also have some predicate about S, then because the variables are universally quantified, for example, if S is f of xy and L is z, then we can set z equal to fxy to unify the variables L and S. After we did the unification, we can rewrite the S to R. And for superposition, we also have additional clauses that can be satisfied if the predicate or if the equality isn't satisfied. So an example interaction with Vampire. Here for equation 100 and equation 8, we can formulate the problem using a TP-TP, which is the format Vampire uses. Sorry. And then Vampire produces a proof. So the proof starts with the first 10 steps here, translating the givens to a normal form. For example, the conjecture, it takes the conjecture and it negates it, and then it uses the choice to get the value that breaks the conjecture. And then it uses superposition. So let's talk a bit more about how it uses the superposition. So it starts by supposing by contradiction that we have the equation, that the equation 100 is satisfied, but we have a counterexample for the target equation 8, that x0 isn't equal to x0, diamond x0, diamond x0. So we start by superpositioning, as you can see in the proof, equation 10 superposes the equation number 1 with itself. And it states that we get x diamond x is equal to x. To see how we get this, we can expand the superposition. So we start with x. Then using equation number 1, this is equal to x diamond y. Now we want to rewrite x diamond y to another term of the same equation for the superposition. So this means we change this to x prime, diamond x prime, diamond y. So now we need to unify these two terms. So that means setting x prime is equal to x diamond x, and y is equal to x prime, diamond y prime. Now if we apply equation 1, this gives that x is equal to x diamond x prime. And if we substitute x prime back, this gives x equal to x diamond x. And now it rewrites using the equation we got at the contradiction assumption to get that x0 isn't equal to x0, and that's a contradiction. It uses here proof by contradiction, despite it not being necessary. This is just a general step Vampire always does, because it lets it prove more general things. It only needs to have one procedure for obtaining a contradiction. So once we have the proof by Vampire, we want to justify what we did in the superposition in Lean. So Vampire says that if we superpose equation A at equation B and get equation C, so this means that equation B is L of S and equation C is L of R. So we want to match up L of S and L of R, so to get an equality, and then apply A to resolve this equality. So this can be approximated by the Lean tactic convert, which attempts to match up the two terms and use equality when the terms don't match up. But sometimes this is too greedy. It attempts to match up too much. For example, in the previous example, it would have tried to set in here, it would have tried to unify this, so it would have set y is equal to x and tried to prove that x diamond x is equal to x. This is false, so it can't prove that. So instead, we created a custom backtracking implementation that does this. Another problem that occurs in translating it to Lean is that sometimes there are unassigned meta variables that we rewrite out. So in Vampire, this isn't a problem because Vampire assumes that all of its types are non-empty. So it can just assume that there is some term and rewrite it out. When we rewrite, for example, in here, we erase the y. We change this to x diamond x prime, and y prime disappears. So in Lean, we need to show that there is some possible value for y prime. Here, we can use the fact that we use contradiction, so we have some x0 floating in a context, so we can just use the assumption tactic to assign some arbitrary value. So, as Vlad has mentioned, this has in fact managed to resolve all of the positive implications in retrospect we now know. And for counterexamples, we also managed to use proof automation, automated theorem provers. For finite counterexamples, automated theorem provers have a finite model building capabilities. Vampire specifically has one, and it can be used to produce counterexamples for many of the finite refutations. We also used it for infinite models. The first use of it for infinite models is using the completeness of Vampire's algorithm. The algorithm of Vampire is complete, so when it finishes but doesn't find a proof, this means that there can be no proof. And this means that the implication is false due to the completeness of Aristotle logic. And in practice, we can translate this argument to a set of rewriting rules. A rewriting rule is simply a directed equality, which means that we rewrite from one side to the other. And confluence means that whenever we have a term, if we only use the rewriting rules to reduce the size of the term or not change it, we can get to a normal form for every single term. So if we have two terms, if we want to check whether the equation implies that they're equal, we reduce both of the terms to a normal form and check. And if we show that they aren't equal, then necessarily the equation doesn't imply that they're equal. This part wasn't done automatically; it was done manually. Okay. Okay. So this managed to resolve some of the anti-implications, but an anti-implication that we struggled with for a couple of days, we tried maybe 10 different methods of proof and of constructing counterexamples, and none of them worked, is the asterisk equation. The asterisk equation, which is equation number 65, is defined as x is equal to y diamond x diamond y diamond x, and the question was whether it implies the obelisk equation. This is equation 1491. For finite magmas, we managed to show very early that it implies it, but for infinite magmas, we got stuck on it for a fairly long time. Eventually, we managed to come up with a method of proof that managed to resolve it, and it also generalizes to resolve many other refutations. The method, as far as we know, is novel and was developed in this project. It lets us decide the equational theory model of an equation. So the method works by having a set of rules. A rule is some kind of if-then condition, where the if is a list of hypotheses. Each hypothesis has the form AI diamond AJ is equal to AK. And the conclusion can have either the form of AI is equal to AJ, or it can be AI diamond AJ is equal to AK. Sorry. We consider partial binary operations diamond, and we want to continue them, to complete them to a total binary operator, maybe adding some more values to the base set. This is we call a rule set in which this can be done a valid rule set. We also assume that the partial binary operator starts as finite. So we also have two other properties of rule sets. We say that a rule set is necessary for a given equation if all of the rules in that equation if the equation implies all of the rules in the rule set. And we say that the rule set is complete for an equation if it's both valid, necessary for the equation, and when the operator is total, it implies the equation. And because we wanted to translate this to first order logic to enable automated theorem provers to work on this, we represented the partial functions using a predicate diamond A1, A2, A3, which meant that A1 diamond A2 is equal to A3. So this means that we also need to have an additional rule for the function being single valued. Okay, so if we have a complete rule set for an equation, this gives us a decision procedure for the equational theory model of that equation. Because if we have an equation that we want to decide, we can assign a variable for each intermediate value in the equation, and we also have the original variables. And this has some finite number of variables. Now we can repeatedly apply the rules, and because we only have a finite number of variables and want to introduce new variables, this will eventually finish. Either we eventually show that the left-hand side and the right-hand side of the equation that we want to check are equal. In this case, this means that by necessity of the rule set, the equation also implies that they're equal. And if we don't get that they're equal, then this is a partial operator that is valid for a rule set. So by validity, we can complete this to a total operator that gives us a counterexample because for total operators this implies the original equation, but in our partial operator that we specified, we have a counterexample for the target equation. The method we used to show validity, we call it the greedy algorithm or the greedy extension. It works over an arbitrary countable set. At each step, we have a finite partial function, so we can find a fresh value that isn't mentioned at all in the partial function, not in the domain and not in the range. And then if we have some A diamond B that isn't assigned and we want to assign it, we will set A diamond B is equal to C. And because the set is countable, we can iterate all of the possible pairs, and at the end we will take a limit to get a total operator. Adding A diamond B equal to C alone isn't sufficient because this can break new rules. If that's all we do, then that will obviously not work very well. So when we add a new value, we will also create a new operator. And whenever we have a rule that the conclusion of it is of the form AI diamond AJ is equal to AK, we will try to set AI or AJ or AK to see if it gives us any new values about equations operating C, about equations involving C. So if the original operator satisfies all of the hypotheses, and the conclusion has, including A diamond B is equal to C, and the conclusion has C somewhere, then we will also add that rule. And we want to prove that the rules are, we say a rule set, this shows the rule set is valid, only if this operation of partially applying the other rules, still preserves the correctness of the rules on the equation, on the magma. So let's give an example of this method. Consider equation 1648. This is the equation x is equal to x diamond y, diamond x, diamond y, diamond x. And if we turn it to a rule, we will create a variable for x diamond y, so that will be x diamond y is equal to a. And we will create a variable for x diamond y, diamond ay, so that will be a diamond y is equal to b. And that means for the equation to be correct, we need to have a diamond b is equal to x. So we will later see how to arrive at this, but if we add the rule for left injectivity, that is, if a diamond x is equal to y and b diamond x is also equal to y, then a must be equal to b, then this becomes a complete rule set. So let's see how the greedy extension method actually works in this, and how this refutes equation number 3253, which is x diamond x equal to x diamond x diamond x diamond x. So we can relabel the variables in the rule. To make it more clear what we are doing, we will relabel them to if x diamond b is equal to a and a diamond b is equal to c, then a diamond c is equal to x. So at the start, to give a counterexample for the target equation, we will use this finite model, this partial operator, And you can check that it satisfies both of the rule. It satisfies this rule and also left inductivity because there is only one term at each row. And now we will attempt to add new values. So we will start at 2, 1. We will add here the value of 4, that's the fresh value. And because, yes, someone raised his hand. Oh, never mind.
Just keep going.
Because
You're over time anyway.
Yeah. Oh, sorry. Because y diamond y is equal to 2, 1 diamond 1 is equal to 2, this satisfies our hypothesis for the rule, so we need to set 2 diamond 4 is equal to 1. Now we will also add 5 and 6 and 7. For 7, again, we need to set 1 diamond 7 equal to 2 because of 2 diamond 4 equal to 1. And we will also add 8 and 9 and 10. We will also need to add fresh values for them. And this method can go on forever. And if we take the limit, this gives us a total binary operator, so we can turn this to a magma. And this gives a counterexample for this implication. So now let's see how we create the rule set, how we obtain it.
So we don't
So
really
we'll
have time, unfortunately.
Oh.
Can you just wrap up?
Okay.
Is that okay?
Okay. So we have a method using Vampire to iteratively add new rules to obtain a complete rule set for a given equation. And the method works by essentially finding a counterexample at each step, and then from the counterexample concluding what rules it needs to add. Sometimes this adds rules that are too complex or overly complex, so we will minimize them to get the best rules that we can. In addition to this, to the automated theorem provers, the project also developed many more theoretical tools. Like using linear operations was very successful at resolving some counterexample or some refutations. Translational invariant magmas, where the operation is defined by x plus f of y minus x, turn our magma equation to a functional equation, which can often be easier to handle. Magma twisting is also a useful way to get a new magma from an old magma. And magma cohomology was also developed recently and is similar to group cohomology. Additionally, there were many, many different techniques that were developed only for specific equations, and I strongly recommend to read a paper when it is eventually released to see about them. So in conclusion, we've seen the methods used in the Equational Theories Project, and how it shows that proof assistants like Lean can let us run large-scale mathematical projects where everybody can contribute, even without prior expert knowledge, without compromising any of the correctness and even achieving it in more correctness than in usual mathematical research.